All right, let's talk about something that's at the absolute heart of communication engineering. You see, if you work with any kind of real-world system, you know the signals we deal with are never, ever perfect. They're always swimming in a sea of noise. So understanding probability and random processes, it's not just some abstract math exercise. It is the fundamental toolkit you absolutely need to pull a clear, coherent message out of all that chaos. Okay, so here's how we're going to break this down. First, we'll get a grip on the core problem, this battle between our perfect signal and all that uncertainty. Then we'll build up the language we need to actually describe randomness mathematically. After that, we'll look at the common fingerprints noise leaves behind, see how it behaves over time, and then finally, we'll get to the fun part, the powerful tools we use to analyze it and ultimately beat it.
So, let's start at the beginning. At the end of the day, all of communications engineering comes down to one thing: a constant fight between the nice, clean signal we want to send and all the unpredictable, random garbage that gets piled on top of it along the way.
And this image, well, it just says it all, doesn't it? On the left, that's our X of t. That's the pristine digital data we sent out, perfectly square, perfectly predictable. But on the right, that's Y of t. That's the mess the receiver actually gets to see. It's rounded, it's distorted. And you can see those little asterisks where the noise was so bad it actually flipped a bit, causing an error. Every single dropped call, every glitchy video, every corrupted file, it all starts with a problem that looks exactly like this. So to even start thinking about this, we have to split the world into two types of signals. First, you've got your deterministic signals. These are the easy ones. Think of a perfect sine wave. You can write a simple equation for it, and you know exactly what its value will be at any point in the future. The other type, the random signal, like that noise we saw, is the complete opposite. You have no way of knowing its exact value a millisecond from now. The only thing we can do is describe its general behavior, its tendencies, using the language of probability. We can't predict a specific outcome, but we can predict the odds. And this leads us to the critical question, right? If the noise is fundamentally unpredictable, how on earth do we build a reliable system? And the answer, the key to everything we're about to discuss, is that we stop trying to predict the exact noise voltage at any given microsecond. That's a fool's errand. Instead, our goal is to model and predict its statistical character. And for that, we need the right tools. So if we're going to start to tame this randomness, we need a formal language to talk about it. And in the world of probability, that language starts with a concept you've probably heard of, the random variable. A random variable is really just a way of assigning a number to a random outcome. You know, if you roll a die, the random variable is just the number that lands face up, 1, 2, 3, 4, 5, or 6. That's a discrete random variable because there's a countable number of outcomes. But if we measure the voltage of a noise signal at one precise instant in time, that voltage could be any value within a certain range. That makes it a continuous random variable. And this split between discrete and continuous is really important because it dictates which mathematical tools we have to use. Now, for those continuous variables, our workhorse tool is the probability density function, or PDF. You can kind of think of it like a probability landscape. The high peaks on the map are where the values are most likely to occur, and the low valleys are for the really rare outlier values. So the higher the curve, the more likely it is we'll measure a voltage in that specific neighborhood. And this is where the theory hits the road. Looking at this Gaussian curve, the shape itself tells us a physical story. The peak is sitting there around 1.3 volts. That tells us the most probable voltage we're going to measure. But just as important is the width of the curve. How spread out is it? A really tall, skinny curve means the noise values are all tightly clustered. The noise is weak. A short, wide, flat curve, that's bad news. It means the noise is powerful, fluctuating wildly all over the place. Now, instead of looking at the whole PDF curve all the time, we often just summarize it with a couple of key numbers. First, there's the mean, which we call mu. That's simply the average value. For us, that's like the DC component of our random signal. Then you have the variance, sigma squared. This measures the spread. And here's the absolute killer connection for engineers. Variance isn't just a math concept. It is physically equivalent to the average AC power of the noise. More variance is more noise power, period. Okay, quick sanity check. A fundamental rule of math is that the total area under any PDF has to add up to exactly 1. So what physical truth does that represent for us? Well, it means that when we go to measure the noise voltage, we are guaranteed to get some value. The probability of the outcome being something is 100%. It has to exist somewhere on that number line. Now here's some fantastic news for us engineers. Randomness isn't always a complete, chaotic mystery.
It turns out that different physical sources of noise produce very specific, recognizable statistical patterns, or what we call distributions.
Think of these as the big three, the usual suspects when you're hunting for sources of error. Gaussian is the king. It models thermal noise in any electronic component. The uniform distribution is perfect for modeling the rounding error you get in analog to digital converters, what we call quantization error. And the Poisson distribution is all about rates. It's fantastic for modeling things like the arrival of data packets at a network router.
So, why is this Gaussian distribution so darn important in our field? It's because of a really profound idea in mathematics called the central limit theorem. What it says, basically, is that if you add up a whole bunch of small, independent random things, the result will almost always look like a Gaussian distribution. Well, what is thermal noise in a circuit? It's the random, jiggling motion of billions and billions of electrons all added together. It's the perfect physical example of the central limit theorem in action. And that's why this bell curve is our most important model for noise. So let me ask a really practical question. Why do we care? What's the big advantage of knowing the noise is specifically Gaussian instead of just throwing our hands up and saying it's random? Well, because if we know its exact mathematical shape, we can do amazing things. We can precisely calculate bit error rates. We can design optimal filters and receivers that are specifically tuned to fight back against that exact type of randomness. We can turn the tables on it. Now, everything we've talked about up to this point, the random variable, the PDF, it's all been like taking a single photograph, a snapshot of the noise at one frozen moment in time. But we know real noise isn't static. It's a movie. So now we have to make that leap from the snapshot to the full motion picture. And this distinction is absolutely fundamental. A random variable, let's call it x, gives you the noise voltage at, say, exactly 1 second. A random process x of t is a function of time. It's a description of the entire collection, or what we call an ensemble, of every single possible noise waveform that could ever be generated. It's not just one timeline, it's the statistical story of all possible timelines at once. Okay, analyzing an entire ensemble of functions sounds incredibly complicated, but we often get to make a hugely powerful simplifying assumption. We can assume the process is stationary. A wide-sense stationary, or WSS, process is one whose basic statistical personality doesn't change over time. Its average value stays constant, its power stays constant, and thankfully for a lot of systems operating in a stable environment, this assumption holds true. It basically means the nature of the noise we're fighting today is the same as the noise we'll be fighting tomorrow. So let's connect that back to the real world. If we make that assumption, if we say the noise is stationary, what are we really assuming about the physical system itself? Well, we're assuming the environment is stable. We're assuming the temperature of our amplifier isn't bouncing up and down, and that nobody is turning on a big motor right next to our receiver, because those kinds of things would change the statistics of the noise over time. And this brings us to the grand finale, the real payoff for all this theory. Now that we have the concept of a stationary random process, we can unleash two incredibly powerful engineering tools that we use to analyze and ultimately defeat noise. Tool number one is the autocorrelation function. It sounds complicated, but it asks a really simple question. If I know the value of the noise right now, how much does that tell me about what its value is going to be a tiny fraction of a second from now? If the autocorrelation function is a big, sharp spike that immediately drops to 0, it means the signal is changing incredibly fast. It has no memory. The future is completely decorrelated from the present. But if it's a wide, slow-rolling hump, it means the signal changes slowly. It has memory. Our second tool, which is just as important, is the power spectral density, or PSD. While autocorrelation looks at the signal's structure in the time domain, the PSD gives us a totally different view, the frequency domain. It's a chart that answers the question, where is all the noise power located in the frequency spectrum? And this is the key to filtering. Because if our precious signal is living at one frequency and the noise power is all concentrated at another, well, we can build a filter to surgically remove it. And right here, this is one of the most beautiful and powerful relationships in all of signal processing. It's called the Wiener-Khinchin theorem, and it states that these two different views of our signal, the time domain view from autocorrelation and the frequency domain view from the PSD, they aren't independent. They're two sides of the same coin, linked together perfectly by the Fourier transform. If you know one, you can always calculate the other. You can translate between these two worlds. So let's bring this all home. The entire workflow, the reason we do all of this, is right here. We can take a real-world noise signal and measure its time domain properties to find its autocorrelation.
Then we plug that into a computer and take the Fourier transform to get its power spectral density. And once we see that frequency plot, we can see exactly where the noise power lives. We can then design a digital filter that cuts out those frequencies while letting our desired signal pass through unharmed. That is the power, and that is the entire point of this incredible field.